In the previous video, we saw and we introduced the pull-up network and the pull-down network, and we saw some examples on them. Let's now take some examples on how to design a complete logic gate. And the complete logic gate, as we described in the beginning, you have to design both the pull-up network and the pull-down network, because the pull-up network is responsible for the cases where Y will be high, the output will be high, and the pull-down network is responsible for the cases where Y will be low. So you cannot design only one of them and leave it. You have to design both of them together, okay? So, for example, let's start with the NOR gate. If we want to design a NOR gate, and the NOR, the equation is the output equals the inputs, and let's assume that we have two inputs only here, A or B or bar. A or B or bar. So inverted. So here, if we want to design the NOR gate, you want to design the pull-up network of the NOR and the pull-down network of the NOR. And in order to design the pull-up network and the pull-down network from the equation, as I said in the previous video, this is the tricky part. You have to try to put the equation in the standard form of the pull-up network to design the pull-up network. And you have to try to put the equation in the standard form of the pull-down network to design the pull-down network. So let's start with the pull-up network. The pull-up network says that you should write the output as a function of the inverted inputs. Here we have the output as a function of an inversion of the inputs, but this is not the inverted inputs. This is not a function of the inverted inputs. This is a function of an inversion of a sum of the inputs. This is not a standard form. The standard form says that you should have A bar alone and B bar alone and C bar alone. So you have to write this as, using demorgan's law, you can write this as A bar and B bar, right? So now you are in the standard form. Now you are in the standard form because the Y is a function of A bar and B bar. In this case, you can plot the pull-up network by saying that you have an AND, you are following the standard equation, of course, you have an AND, then you should have two transistors, both of them CMOS, in series. And since you are following the standard equation, then you are going to put here the first input A and the second input B without inversion. Why without inversion? Because you are following the standard form. So now this is the pull-up network. The pull-down network, in order to plot the pull-down network, you have to try to reach to this standard form. How to reach to this standard form? Take the inversion. Take Y bar. Y bar will be A or B. Very good. We are already now in the standard form because we have Y bar as a function of the inputs without inversion. In this case, we can directly go and plot the pull-down network, and we say that the output will be low if A is high or B is high. So this is, since we have an OR in the equation, this will result in two parallel branches. And since we are following the standard equation, the first transistor will be operating if A is high, and the second will be operating if B is high, and we put them without any inversion. Why again? Because we are following the standard form. We are following the standard form, whether for the pull-up network or for the pull-down network. So for the pull-up network, we found that we have two transistors in series. For the pull-down network, we have two transistors in parallel. There is a lesson that we will learn here that will help us also in the design of logic gates. We'll notice always that the pull-up network and the pull-down network, they behave opposite to each other, which means that any series connection here, it will be converted to parallel connection here. And any parallel connection here, it will be converted to a series connection here with the same inputs. So again, if you design the pull-up network and you find that you have a series connection, you know before you process the equation of the pull-down network, you know that you will get a parallel connection in the pull-down network. If you have a parallel connection in the pull-up network, you know before you process the equation of the pull-down network, you know that the pull-down network will have a series connection, and so on. So we will notice that there is a behavior that is opposite between opposite behavior between the pull-up network and the pull-down network. Any series connection here will appear as parallel here. Any parallel here will appear as a series here. So you have two ways to design the network. Either you process the equation of the pull-up network and the equation for the pull-down network. This is one way, like what we did here. Or the other way is you process one of them. For example, you process the pull-up network and then you reverse all connections to get the pull-down network. So you have two ways. Either you process the equation of the pull-up network alone and the pull-down network alone, or you process one of them, not necessarily the pull-up network, any one of them, and then the other you can get it by reversing the connections. So this is the lesson that we learned here. Let's take another example. Let's take the NAND gate. The NAND gate says that the equation for it says A and B bar. So in order to design our gate, let's try to reach the equation, the standard equation of the pull-up network. The standard equation of the pull-up network for the pull-up network, standard equation can be written as y as a function of A bar, B bar. So we can use De Morgan's law here in order to write A and B all bar as A bar or B bar. Now we are following the standard equation for the pull-up network. So the pull-up network will be two parallel branches, two parallel transistors. Don't forget that both of them must be PMOS. So we put a bubble here. And since we are following the standard equation, we put A and B as inputs. Even if you have A bar and B bar in the equation, but you are following the standard form, so we put A and B. And this is the supply voltage. This is the output Y. Now, for the pull-down network, we have two options. Either we reverse the connection, so here we saw that we have a parallel connection, two transistors in parallel, so you know directly that there will be two transistors in series here, NMOS, with the same variables, A and B. So this is one way, by reversing the connection. Or you can process the pull-down network equation. Pull-down network equation, take Y bar, we need Y bar. So Y bar will be A and B, right? From this equation, Y bar equals A and B, which means that this is the standard form of the pull-down network, which means that since we have AND, which means that Y will be low if both A is high and B is high. So these are two transistors in series. The input to the first transistor is A and the second transistor is B. So you will get exactly the same result. So you have two options. Either after designing the pull-up network, either you reverse the connection or you process the equation of the pull-down network. And that's it for this NAND gate. Okay? And so the lessons here, that OR gives you parallel, AND gives you series, the pull-up network and the pull-down network are opposite to each other, and the standard form of the pull-up network is that you write the output as a function of every input inverted, and the standard equation for the pull-down network is that you write the output inverted as a function of all the inputs without inversion. And the other lesson is that if there is a variable that doesn't follow the standard equation, then you have to invert it in your circuit. Okay, let's take another example. Let's take more complicated example. By the way, one of the questions that is usually asked is how many transistors used in implementing your logic gate? And this is a very valid question, because how many transistors matter? How many transistors? This is something that matters, okay? Because we need to minimize the number of transistors as much as possible to make the chip as small as possible, and we can implement many gates on the same chip. You have to minimize the number of transistors in each gate, right? So for example here, and in the previous example, we used 4 transistors, 1, 2, 3, 4. So we have 4 transistors. and even in the NOR gate also we used for transistors. Let's now take another example. An example says design a logic gate Y bar equals A and B or CD. So this is a logic gate that we need to design. Let's remove this for now. So again, we are going to start with the equation, the standard equation. So in order to design the pull-up network or the pull-down network, you have to write the standard equation. It's good here that we notice that the given equation in the question, it follows the standard form of the pull-down network, the standard form of the pull-down network, which is Y bar as a function of all the inputs without inversion. So we can start with the pull-down network. We can start by designing the pull-down network. So the pull-down network will be, so this is Y, A and something, A and some block. A and some block, which means that we have a transistor in series with a block. We have a transistor operated by A, and some block means it's in series with some block. So it's in series with something. And then let's look at this something. This something is B or something. B or means that we have two parallel branches. So A in series with a block. A in series with a block. This block, it has two parallel branches. B or the other branch, we have two transistors in series. Again, because we have AND operation, so two transistors in series, C and D. Did you see how I did it? So you simplify it yourself. You say I have A and something. So this is series connection between a transistor A and some block. And then the block, we have two parallel branches, B, and the other branch is C and D. Now, for the pull-up network, we have two options. Either you reverse this connection up, or you use the equation. We'll do both. Let's start by reversing. So here we have A in series with a block. So you expect that up, you will have A transistor that operates with A in parallel with a block. So here A in series with a block, here will be A in parallel with a block. And don't forget the PMOS. Then the block, A in parallel with the block. This block, okay, it's B in parallel with something. Here it will be B in series with something. Then this something, it was C series with D. Here it will be C parallel with D. Do you see how I reversed it? Everything is reversed. Everything is reversed. So it was A in series, became A in parallel. And then here, this block, okay, B was in parallel, it became in series. C was in series with D, it became in parallel with D. You can do the same using the equation. So for example, using demorgan's law, you can say that Y equals A all bar, right? You can take bar both sides. And then using demorgan's law, A and something bar means that it will be A bar or B or CD all bar. And then again, B or something all bar, it will be B bar and something C D all bar, which can be written as A bar or B bar and C bar or D bar. Again, you will find that this equation follows the standard equation of the pull-up network, right? It's the output as a function of every input inverted. And then if you apply it, you'll find that you have two parallel branches, A in parallel with something, so transistor A in parallel with something, then B in series with something, B in series with something, then this something is C parallel with D. So it will give you exactly the same connection that we obtained by reversing the pull-down network. So you can either reverse the pull-down network or you can process the equation of the pull-up network, whatever is easier to you. How many transistors we used here? 1, 2, 3, 4 in the pull-down network and 4 in the pull-up network. Then we have total 8 transistors. 8 transistors in total, right? Let's take one more example before we end this video. Let's try to design the XOR gate. The XOR gate. The XOR gate, its equation is y equals a b bar or a bar b. Here, for this gate, you will find that first, the equation for y, it doesn't follow the standard equation of the pull-up network. Why? Because some of the inputs are not inverted. So it doesn't follow the standard equation. If you try to play any tricks, you will not be able to put the equation in the standard form of the pull-up network. If you try to get the pull-down network, y bar, you take y bar, then you will find that y bar can be written as a b or a bar b bar. The remaining of the two terms, if you remember the logic equations and the truth table, these two terms, they give you the output high, the other two terms, they give you the output low. And always you'll find that if some of the terms appear in the equation of the y, the remaining of the terms, they appear in the equation of y bar. So this will make it easy to you later when you have three variables, for example. When you have three variables and I give you that, for example, y equals a b bar c or a bar b c bar, for example, then you understand that y bar, the equation for y bar, will contain 6 terms, because if we have 2 terms out of 8, if you have 3 variables, you have total 8 terms, 8 different combinations. If 2 of them appear with the y, then y bar will get 6 terms here. So how to implement this circuit, and this you will see in the examples or in the homework, examples in the textbook. It's better to implement the y and then you invert the connection in order to get the pull-down network. Because if you implement the pull-down network using these 6 terms, you will use many transistors. But here you are using only 2 terms, which means 2 branches, each branch with 3, let's say 3 transistors. And when you invert it, then the pull-down network, you will use also 6 transistors in addition to the inverters that we'll discuss later. But if you use this equation to implement y bar, you will have to implement 6 terms. 6 terms means 6 parallel branches. Each branch has 3 transistors. You will use 18 transistors. So it's better to implement the pull-up network from this equation, and then you reverse the connection to get the pull-down network. This is better than implementing the equation itself. So knowing how to write the terms and the equations from the logic design course, this is good for you and will help in the efficient implementation of the logic gates. Anyways, let's go back to our example. We have 2 terms here for y, 2 terms for y bar. If you try to play any tricks, you will not be able to put them in the standard form. So what we'll have to do here is, you will have to implement this equation without the standard form. The output, y, this is for the pull-up network. Now let's implement the pull-up network. It says that we have 2 parallel branches. Each branch has 2 series transistors. Here, in the first branch, we have A and B bar. As we see, the variable A doesn't follow the standard equation, so we put it here as A bar. B follows the standard equation because it's B bar, so it follows the standard equation, we put it as B. The second term, A follows the standard equation, so we put it as A. We put it as A because it follows the standard equation. B doesn't follow the standard equation, we put it as B bar. So here, this is how we implement pull-up network in case of not following the standard equation. The variables that do not follow the standard equation, we put them inverted. Same for the pull-down network. We have two parallel branches. Each branch has two transistors connected towards the ground. NMOS, don't forget. A, B here, they follow the standard equation, so we put them as AB. The other term, A bar, B bar, do not follow, the two variables do not follow the standard equation, so we put them as A bar and B bar. What does it mean that we put A bar and B bar, A bar and B bar? It means that you need to invert A and B first, and then you connect them. So you need to invert the variable A, and you invert the variable B, so you need inverters. So now if we count the number of transistors, and focus with me here because this is very important. If we count the number of transistors in this gate, we'll find what? We'll find that we have 1, 2, 3, 4, 1, 2, 3, 4, 4 plus 4, 4 plus 4, 4 transistors in the pull-up network, 4 transistors in the pull-down network. But notice something, that we will need also an inverter to invert the A, inverter to invert the B, and here also we need to invert the A and B. So we need inverters. Each inverter, each CMOS inverter consists of two transistors. You remember inverter? You remember the CMOS inverter? Each inverter, it has two transistors. How many inverters we need here? Some of you may say we need 4 inverters. I say no. We need only 2 because we need to invert the A once and then we connect it here and here. You don't need to use 2 inverters, you need only 1 inverter to invert the A, and then after you invert the A you connect it to this transistor and then this transistor, and you need to invert also the B once. You don't need 2 inverters for B, you need to invert the B once and you connect it here and you connect it here. So you need 2 inverters. Each inverter has 2 transistors. Then total you will need 12 transistors. So 2 inverters, each inverter has 2 transistors, so 4 transistors, plus 4 in the pull-up network, 4 in the pull-down network, so total 12 transistors. That's it for this video. We'll see you in the next video, inshallah.